Hello everyone and a very warm welcome to this lecture. I hope you all are doing well and stay curious about learning. Today we are going to discuss a very small looking concept but one that plays a very big role in the machine learning and artificial neural network. This concept is called feature scaling. I want you to relax, listen to the story behind it and not worry about formulas for now. By the end of this lecture, you will clearly understand why feature scaling is not optional but essential in the machine learning. Let's start with the simple real life situation. Imagine you are in the classroom where one student whispers very softly, another student speaks at a normal volume, and one student is shouting very loudly. So now, as a teacher, whose voice will dominate the classroom? Obviously, the loudest one. Machine learning algorithms behave in the same way. They listen more to larger number, not because they are more important, but because they are louder. This is exactly where feature scaling comes into the picture. Now, let's understand the formal idea about scaling. Feature scaling is the process of transforming numerical input feature so that they lies within the comparable range or distribution. In simple words, feature scaling makes sure that all input features speaks at the same volume. In real world data set, age may be in the years or income may be in the rupees and distance may be in kilometer. For example, age varies from 18 to 60 and income varies from 50,000 to 50 lakh. Distance varies from 1 to 500 kilometer. These values are not comparable at all. Feature scaling removes this imbalance so that no single feature dominates just because of its size. Now, next question is why what are the feature scaling or why the feature scaling is important? So the main thing is what happens if we do not apply feature scaling. Okay, so without feature scaling, many problems arise. First problem arises large valued feature dominate learning. For example, income will dominate age, even if age is more important. Second problem is gradient descent become slow or unstable. The algorithm keeps overshooting or oscillating instead of smoothly moving towards the situation or the solution. Third problem we have the distance based algorithm like KNN or and K means give biased result because distance calculation becomes unfair. Fourth we have is the in numerical in a neural network, we may face vanishing gradients or exploding gradients, which completely break the learning process. So, without feature scaling, even a good model behaves badly. Next, we have is the with feature scaling. When we apply the feature scaling, learning becomes faster and smoother. Second, optimization becomes stable. Third one we have is the numerical computations become well conditioned, neural network trend more reliable, and the last one, model accuracy and generalization improves significantly. So feature scaling does not change the data, it changes how efficiently the model learn from the data. So this is very important feature scaling. Third we have is the algorithm that strongly requires feature scaling. We discuss these one by one. Now let us connect feature scaling with algorithm. You already know algorithm where feature scaling is critical. Feature scaling is absolutely necessary for artificial neural network ANN because gradient depend heavily on input scale, linear and logistic regression because they use gradient descent. A sport vector machine or SVM because margin depends on the distance. K nearest neighbor or KNN because distance calculation is the core idea. Principal component analysis PCA because variance depends on the feature scale. For this algorithm, skipping feature scaling is serious mistake. Next we have is the algorithm where feature scaling is less important. Okay, so this is also we need to discuss very carefully. Now in an interesting fact, feature scaling is less important for decision tree, random forest, gradient boosting trees. Okay, why these are less important? Because these algorithms do not use distance calculation, do not rely on the gradient descent, split data based on the condition, not on the magnitude. So they are called scale invariant algorithm. And here we have some final takeaways. Let me end all this with a powerful takeaways. Feature scaling does not change informal, it changes how efficiently algorithm learn from that information. In machine learning and especially in artificial neural network, feature scaling is not optional, it is foundation. So in the now we will discuss about normalization, standardization, robust scaling with clear Python examples. So stay connected during the entire lecture. Okay. So here we can you can see common feature scaling and rescale feature to extend fixed range usually from 0 to 1. And here you can see the formula is there. Mathematically, x dash will be equal to x minus x minimum upon x maximum minus x minimum. So this is the required formula. Okay, so this is the formula where you can see x dash is equal to x minus x minimum upon x maximum minus x minimum. So x is the original value in the data set and x minimum is the minimum value from the array and x maximum is the maximum value. Okay, so here you can see is the example we have taken here so that we can calculate these values and quite easy. See this example. Here we have is this vector and the values in this vector we have are 50, 60, 70, 80 and 90. So minimum value in this data set we have is 50 and the maximum value is 90. Suppose that we want to calculate for x is equal to 70. So the scaling value for x equal to 70 we have is we will use the above formula and put all these values and x dash will be 70 minus 50. This is the minimum value, then maximum value minus minimum value, and this is the x value. Okay, so after simplifying we have 0.5. So in this way we can calculate for the all values 50, 60, 70, 80, 90, and after scaling all these values we have this vector. And in this vector you can see the minimum value is 0.0 and the maximum value is 1.0 and all other values lies between all these. So this is the scaled vector. Okay, so this will by using in this way we can easily do scaling for any large data set so that we have the uniform parameters with respect to all the parameters. Okay, so here now I can delete this, minimize, come here. We have the manual example how we can use by Python. Okay, so first we need to create a vector. Here we have created the vector x is equal to by using the numpy. First you need to import numpy as np, then we store the value which we have chosen in the previous example. Okay, so the values are 50, 60, 70, 80, 90. Then x is equal to, we will run this code, control and enter. Yeah, so these are the values you can see. Now we need to compute minimum and maximum value. So x minimum is the minimum from this vector and this will give us the maximum value from the above vector which we have chosen here. So minimum and maximum function from the numpy we are using here, x dot minimum function and x dot maximum function. Okay, and these values will be stored inside x minimum and x maximum vector variables which we assign on the left hand side, and this value will print the values. Control and enter. Yeah, these are the output values. This is the minimum value and this is the maximum value. Now we will apply the minimum maximum formula which we have discussed earlier. So x normalized is equal to, this is the numerator, x minus minimum value divided by maximum value minus minimum value. So this will compute the normalized value and you can see control and enter. Okay, so these values are from 0 to 1 and the other values lies between 0 and 1, 0.5, 25, 0.5, 0.75. Okay, so here is the step for verify the range. If you want to verify, we can verify the range. So x underscore normalized dot minimum, this will give the minimum value, and this will give the maximum value of the above vector. You can verify in this way. So the minimum value is 0.0 and maximum is 1.0, because sometimes we have very large vector. So here we have very small size of the vector, but many times we have 1000 values, and it is very typical to cross check. Okay, so we can use here directly this range, minimum and maximum value. So this will give us the respective values. Now here we have one more formula in example number 2, normalization using scikit-learn. Okay, so whenever we use the training model, or we want to develop, so machine learning models are there, and one by one we can use them. So before using these, we need to import a address space. So here we are import and prepare the data set. So from scalar dot preprocessing, import minimum maximum scalar. Okay, minimum maximum scalar we are required to import here, and also we are using the numpy as np. This is the data set. You can see this is the data set feature matrix. Two variables are there, age and income. Okay, so we are storing the values by using the array vector. The age are 18, and this is the income. Okay, 2 lakh, then 22 and 50 lakh. Here is 25 and 1 crore. Okay, so when I will execute control and enter, then what we need to apply minimum maximum vector. Okay, so here you can see minimum maximum scalar, and as soon as you will use for this, and after that we need to fit the transform. So scalar dot fit underscore transform. So the value minimum maximum will be stored at this place, and we are using this one. This will fit automatically scaled. Okay, so when you will run this code, control and enter, you can see at this place the edges 18 and 25. Okay, so this is the minimum and this is the maximum value, and this is the 0.5714 something. Okay, so this is the scaled value for this one, and this is the another vector, second variable. Okay, and with respect to all these values, the scaled value are 0, 0.375 and 1. So you can see we can easily compare, and very less difference is there. Otherwise here we are not able to compare all these, because these values are very high, these are small in size. So but here after scaling we have these values are comparable. Okay, range are absolutely same, 0 to 1 and 0 to 1. After that we can check a minimum and a maximum parameters. Okay, so here x scale minimum, x is 0, and x scaled maximum. So when you will use this command, this will return minimum and maximum value. Okay, for so here you can see 0 0. So age and second value is for income. Okay, so both are minimum, and here these are the maximum values. After that we can have the correct uses with the trend test split. We are using the same library as we use in the above, this one, and we need one more library from sklearn.model underscore selection import trend underscore test split. So here we will train the model. Okay, we have x is equal to np.array, values are 18, 22, 25, 30, then 20, 2 lakh, 5 lakh, 10, 15. Okay, so these are the x values, and after that we have the y. The values inside y we have is 0, 1, 0, 1. So these are the target value, and these are the input values. So here we will train the model. So this is the syntax: x train, x test. Remember this one. Always we use in this way: y train and y test. Then we will use the function train underscore test underscore split. Okay, the values are x, this input value, then y, and test size we have to choose the test size, which is 0.25%, and random state we are taking 42. Okay, after that we are using here scalar minimum max scalar, and x10 scaled we are given at this place. Scalar dot fit underscore transform x10. Then we have the x test scaled is equal to scalar dot transform x test, and here we will compare the values x10 scale and x test scale, both we are comparing here. So when I will execute this shell, and you can see the values are lies x trend scale value are 1 0 0.583 and 0.3. So first these are the values for the x trend, and this is the x test we can see, and these are the that of for first column represent for the age and second for the income. Okay, and these are the test scaled value which are 0.333 and 0.230. So in this way we can easily compare these values. Now the question arises, why normalization is useful in artificial neural network? Keeps input within the bounded range. As you can see in the above example, the range is bounded between 0 to 1. Okay, prevent neuron saturation in the sigmoid or 10H activation functions, improves training stability, and commonly used for image data 0 to 255 to 0 to 1. When not to use min-max scaling, presence of the strong outliers, stemming data with the unknown minimum maximum, and when unbounded features distribution are acceptable. Next we have is the most important scale, Z-score scaling, or we can say usually standardization. Okay, standardization transform data to have the zero mean and unit variance. Okay, mathematically expression we have x dash is equal to x minus mu upon sigma, where mu is the mean and sigma is the standard deviation. Okay, and here we have the numerical example we can discuss here. So we suppose that the vector x is equal to 10, 20, 30, 40 and 50. These are the values, and mean is 30 and their standard deviation is 14.14. Suppose that we are taking x is equal to 40. So by using the above formula, we have x dash is equal to 40 minus 30 upon 14.14. So after simplifying, this is approximately 0.71. Okay, so what are the characteristics of this? We have the centered around 0. The values mostly will be centered about the 0, and unbounded values less sensitive to extreme values than minimum maximum. We can use these in deep artificial neural network with the ReLU and linear and logistic regression, support vector machines, and as well as PCA. So here are some applications of the standardization and Z-score. Mean standardization is the feature scaling technique that transforms numerical data so that each feature has mean is 0 and standard deviation is 1. This ensures that all features contribute equally to the model learning, especially in the gradient based and neural network model. Here we have the example, and by using the NumPy. Okay, so first we need to require data set. Okay, so this is the same way as we use in the previous one. Import NumPy as NP. Okay, then this is the array when you will execute. Yeah, then after step 2, we are required to compute mean and standard deviation according to the formula requirement. So mean is equal to, we have is np dot mean. This will calculate the mean of this vector, and np dot std, this will compute the standard deviation of this vector, and mean comma std we are using here to print the value. Control and enter. So you can see the mean of the above is 30 and that of standard deviation, which is 14.142135 and so on. Now we will apply here Z-score formula. Okay, so this is the formula and syntax for the formula: x minus mean upon standard deviation. So this will compute the value and will store inside x underscore standardized. Okay, and this is used here to print the value. So when we will apply, so all the values of x will pass through this formula, and will return the values. When you will execute, you can see these are the values, and this is the central value. Okay, 0 is the central, and on the right hand side you can see the values are positive, and on the left hand side you can see these values are negative. Okay, these values are negative magnitude. Okay, and these are positive. Then if it is required to verify, we can do easily here np dot main access standardized, np dot std access standardized. When you will execute, control and enter, so you can see here the mean is 0. When you take the mean of this, so this is the 0, this is negative, and this value is positive, this is negative, and this is positive. So when you will add all these values, the sum becomes 0. Okay, and the standard deviation is about 0.9999 and something. Okay, so this is the standard deviation. If you want to apply a scikit-learn as we do in the previous example, we can do here also. Okay, so we are required the same library from the machine learning, and numpy is np. Okay, the feature matrix we are taking age and income. These are the same values, same example we have. So when we will execute, control and enter, the value will return at the place. Then we will apply the standard scalar. Okay, this is the package which we are using, standard scalar, and will store inside the address place, and then we will fit transform. Okay, for x. So when you will run this code, control and enter, you can see these are the values which are lies between, some are negative and some are positive, scaled value. Okay, similarly for these values are, some are negative and some are positive. Okay, and if you need to check the mean and standard deviation per feature, we are using the same method as you can see here. Xscale dot mean, x is 0, and here is also xscale dot std. First is used for the mean and second is used for std. X is equal to 0 means column. Okay, so when you will execute, and we can have these values. Okay, next we have is the correct uses with the 10 test split. This is the same as we do for the first method. Okay, correct, for that we are using the same libraries, and this is the same data set. Okay, and the x inputs are age and income. These are the target value. Okay, output values. So you can see here the same x test, x10, x test, y10, y test, and is equal to 10 underscore test underscore split, and these are the same values. Okay, so x comma y test size we are taking 0.25, and random underscore state is 42. Then after we need to standard scalar function we are required to use, then we will fit the transform x10 and scalar transform x test. Okay, and here both will print x10 scaled and x test scaled. Control and enter. Yes, so here these values are the x10 scaled and these values are x test scaled. Okay, so why standardization is preferred in artificial neural network? These points are keep in mind. Keeps input centered around the 0. Okay, and improves gradient descent convergence. Works well with the ReLU or weakly ReLU activation. Reduces risk for exploding or vanishing gradients. Next we have is the very important scalar robust scaling. Okay, or outliers resistance. Definition: use median and interquartile range IQR. Robust scaling is the feature scaling technique designed to reduce the influence of outliers. Okay, robust scaling is needed. Consider that the data we have is 30,000, 35,000, 40, 45, and you can see the 2 lakh, 2 crore, 20 lakh. Okay, so this is the data set, and the mean and maximum are distorted by the extreme CO salary. Minimum access standardization failed to represent typical employees. Robust scaling focuses on the central data mass instead of using the mean and the standard deviation, which are very sensitive or to extreme values. It uses median. Interquartile range, you can see the Q3 and Q1, so we can use this one. This makes the scaling robust to extreme or skewed data. Mathematically expression for the same when we are required to use, we have x dash is equal to x minus median upon IQR. Okay, here is the example scenario. Salary with the one CEO earning extremely high income. Robust scaling prevent that one extreme value from the destroying the entire feature scale. So the use cases are there: financial data, real world noisy data set, heavily tailored distribution. And here we are using one example, manual robust scaling using the NumPy. So first we are required to store the value in one parameter, and by using the NumPy we can store all these values inside x variable by using np.array function. Okay, so these values are stored inside x. Then we are required to compute the median and IQR. So median is equal to, we will have np.median. So to calculate IQR, we are required to calculate Q1, which is the np dot percentile x 25%. Okay, and Q3 is 75%. You can see, and syntax function you can see also np dot percentile. This function you have to use, and x is the vector which we have stored the values by using x, and this is the 25% and this is the 75%. Okay, so IQ R will be equal to Q3 minus Q1. This is the formula to calculate IQR. So here we are required to print these all values: median, Q1, Q3, IQR. So when we will execute this statement, control and enter all these values after computing, we have at its place. So this value is the median, this is the Q1, this is Q3, and this is IQR. Okay. Now we will apply the robust scaling formula, and you can see this is the robust scaling formula: x minus median upon IQR. So just we need to pass all these values which are computed at a place. Automatically, when we will execute this function here, we will pass all the values, and when you will execute, the values will return. Here you can see -1, -0.5, 0, 0.5, 196. Okay, so these are the robust scaling values, and we try to put here interpretation of the above also. So center values are scaled reasonably, outliers does not dominate the scaling, and relative structure of most data is preserved. Okay, so these are the some interpretation about this robust scaling. The same we can do by using the scikit-learn. Okay, so the process will remain same as we do in the first example, first method and the second method. So here is also the same. We are required to import this module for machine learning, and this is the NP library, and these are the input data set. So when you will execute, the data set and the libraries will imported, and data set will return at the page. Now we will apply the robust scaler. So here we are using the robust scaler, right, package, and here is the robust scaler. So then after scalar dot fit underscore transform, and this will return the scaled value by using the robust scaler. So you can see these are the values, and all these values are comparable. If you need to verify the robust properties, so we can do here import numpy as np, and this is the np.median x scaled 0, and control and enter. You can see the values are 0, 0. Next question arises: when to use robust scaling? Financial data set, income, price, transaction we can use. If we have the medical data set with extreme readings, real world noisy data set, or we can have skewed or heavy tailed distribution, in that case we can use robust scaling. Robust scaling in artificial neural network prevent extreme weight update due to the outliers, improve training stability, and often used in pre-processing pipelines before artificial neural network. And here is the correct usage with the train test split. Here you can see the example. So what we are doing here, this is the package for the machine learning. Okay, train test split, and here we are using the from sklearn.preprocessing import robust scaler. Okay, according to this module. This is the same data set. Okay, x vector have the two variables, one is age and other is income, and here we have the target values or the output values. Based on these values, we will train and test x and y both vectors. Okay, so this is the same syntax as we use in the previous two examples. Okay, x train, x test, y train, y test. So this order will be remain always same. Then we are using the function train underscore test underscore split, and this is the x vector, y, then test size 0.2, or you can take a 0.25 depend upon your size or test size. Random size we are taking here 42. Okay, so then after a scalar we are using robust scalar, and a scalar dot fit transform x10, and a scalar dot transform we are using x test, and the values will print at its place. Control and enter, this will compute to and return the calculated values which can be seen at its place. Scaled values, these are the scaled values for training as well as for test. Here is also we can have feature scaling in the artificial neural network. Just 1 minute. The artificial neural network, you will soon realize that artificial neural network is extremely sensitive to the scale of input values. Think of the neural network like a team of the students trying to learn together. Each student adjusts their understanding little by little based on feedback. Now imagine one input feature sends a very large signal, another input feature send very small signal. What happens? The network starts paying attention mostly to the loud signal and ignores the softer ones. This leads to uneven learning. This is exactly what happens when we train the artificial neural network without feature scaling. Okay. So first, from slow convergence, because features are on the very different scales, gradient descent struggle to find the optimal direction. The network takes a smaller step in some directions, larger uncontrolled step in other. As the result, training becomes unnecessarily slow. Okay. The second problem is oscillating gradient. Instead of smoothly moving towards the minimum error, the gradient keeps jumping back and forth. The learning curve becomes unstable and training does not settle properly. And the third one we have is the most dangerous problem, vanishing or exploding gradients. Some gradient becomes extremely small and stop learning. Some gradient becomes extremely large and break learning. This problem is very common in deep neural network, and when input features are not scaled. With the feature scaling, we are now come to the conclusion. Okay. So now let us see what happens when we apply proper feature scaling before training an artificial neural network. First we have is the fast convergence. Okay, when features are on similar scale, gradient descent moves smoothly, the network reaches optimal weight faster, and training time is reduced significantly. Okay, and then balanced gradient flow. All input features now contribute fairly. No feature dominate just because of the magnitude. This keep the learning stable and predictable. Okay, and improved generalization. Third benefit is improved generalization. Okay, the network learns real pattern, not numerical biases. As a result, the training performance improve, test performance improve, overfitting is reduced. So best practices in artificial neural network is very important. Now let me share some practical rules that you should always remember while working. Okay, choosing the right scaling method. When choosing the feature scaling, always consider the activation function. Okay, so if you are using sigmoid or 10H activation function, these functions work best with bounded input. So we use normalization. If you are using ReLU or weekly ReLU, okay, these functions work best with zero-centered data. So we use standardization. If you are working with images in CNN, pixel values are usually between 0 to 225 to 55. Okay, and we scale them 0 to 1 using the minimum max scaling. Okay, so here we have is the spoken table. You can see in the activation function we have our sigmoid, tangent, and right hand side we have recommended scaling, normalization, and ReLU or weekly ReLU we will use standardization, and CNN we will use minimum maximum. Okay, and finally let me conclude this session with one key message. In artificial neural network, feature scaling is not just pre-processing, it is the requirement for stable and meaningful learning. If feature scaling is ignored, learning becomes slow, gradient becomes unstable, model performance suffer, If feature scaling is applied correctly, training model faster, learning becomes balanced, generalization improve. Okay, so in the next lecture we will discuss about the implement these ideas in the Python and see the effect practically. Thank you to see this lecture entirely.